So, we've got a little bit more to do on Lecture 4.3, DC motors. So remember that we kind of introduced the idea of a DC motor. We dove into the details of how a DC motor is able to convert electrical energy into mechanical energy using the Lorentz force, flowing current through a wire, which was called the armature, that was moved through a stationary magnetic field. Oh, I went ahead and drew these figures nicely now. I sketched them last time, but I went back and drew them. And so this is online now, so if you want to print out the nice drawings, you can. They're essentially the same as the ones that I drew in class, though. And then we talked about permanent magnet DC motors in detail. Talked about the different issues that we would run into, like the direction of the torque reversing on us, and that was a problem. The wires that would wrap, that was a problem. How we solved that with the brushes, and that helped quite a bit. And here was the figure I kind of sketched as well, with the commutator and the brushes, the armature, rotor, and then the stator with the background magnetic field. And then we talked briefly about wound stator DC motors, which are DC motors that have the background magnetic field provided not by permanent magnets but by electromagnets. So they have a coil of their own, and you have to drive current through that coil as well. So there are different ways to connect up the stator coil and the armature, so in the rotor coil. So the three different variations are the shunt, which is a parallel connection, the series, which is a series connection, and then a compound, which is both. And I drew these three, but here are the three drawn nicely in figure 4-5. So that brings us to brushless DC motors, which is the last sort of variant that we'll discuss of DC motors. So brushless DC motors have the acronym BLDC. So if you see BLDC, that means brushless DC motor. They work on principles more similar to AC motors, but require complex solid-state switching that must be precisely timed. So we didn't talk about AC motors, but I'll talk about them for just a moment. The idea with an AC motor is, you know how in the DC motor we have a background magnetic field that's stationary, right? The stator provides a stationary background magnetic field in one direction. And then what we do is, as the armature rotates around, we switch the direction of current so that it keeps the torque going in one direction. With AC motors, the general idea is, let's just rotate the background field around, and then the armature will follow the rotating magnetic field. So we'll create the torque by rotating the magnetic field itself and induce the armature to turn. Now, there are a bunch of different variations of this, but generally there are different schemes for rotating the magnetic field. Using multiple phases of AC is kind of the main method. So, oh man, I'm just going to talk about this for a minute, because in the earlier class I was late because I-5 was like totally a parking lot this morning. I don't know why. Was there?
Yeah, it was like 4 cars in a semi.
Ugh. Hope everyone's okay. It was inconvenient for me, but hopefully not worse for somebody else. So I was late. So I have a little extra time in this lecture. We didn't get as far as I was hoping. So let's talk about AC a little bit more. Move my face out of the way. So imagine that we've got a coil here and a coil here. This one provides a field this way, and this one provides a field that way, okay, like the field lines. And then we have the armature coil in the center still. So I'll draw the armature coil just as a magnetic dipole. So you could imagine that or I mean, you can actually technically do this, but it's just very rarely done with a permanent magnet. So imagine this as a permanent magnet dipole, and it's in this background field. An AC motor, say it's just a two-phase motor. A three-phase is a little bit better for complex reasons, but a two-phase motor is going to have AC going through this coil and AC going through the other coil, but at a phase shift. So I'll start this one out here. They're out of phase with each other, so that we can, using this out of phase AC signal, we can rotate the background field by adding the two fields together. So you can imagine that when this field ramps up and this field ramps down, then the field will be more horizontal than vertical. And when the vertical field ramps up and the horizontal field ramps down, the effective field will be more vertical than horizontal. And using that scheme, you can essentially make the magnetic field go around in a circle, and it'll induce this magnetic dipole in the center to follow that field around in that same circle. Now, the details of how that goes is like, there are a lot, and it's pretty complicated. You can get more and more coils. A three-phase would have a minimum of 3 coils, and you can have a similar scheme where you have all of your signals out of phase with each other, so that they all add to 0. That's the idea with a three-phase. So AC power coming from your wall is single phase. I don't know if it's universally the case. Some houses have 2-phase. I don't know if that's across the board at every residence in the United States. In Europe, I think it's standard that every house has 2-phase. And then you can get 3-phase, though, because 3-phase is what industrial AC power comes in as. So 3-phase is usually not available for consumer products, though, because you have to have a special line that comes in. Yeah?
3-phase is what's in the power line.
Maybe. You might be right.
That's what we learned with
I think that, that's true for some of the distribution networks, but I don't know if it's true for all residential networks, though. It is for industrial. So when you're talking about PV, you're probably thinking about an industrial setting. So industrial power does come 3-phase. Now that I think about it, I'm confident that at least most places in the U.S. have 2-phase, because the special outlets that are for the washer dryer hookups and some stoves special, those are 2-phase. So they do come with that then. But I've never seen 3-phase connected up in a home, and I'll be a little bit surprised if they actually distributed it to all the way down to all the residential networks. But
just in the main power lines, is
Mm.
phase, and then they pull one wire off and lead it to each neighborhood.
Gotcha. Yeah, that would make sense that they would just distribute it as. I think they have to do 2, but 3 is the. If you have any high-powered AC motors, they're almost always going to be 3-phase. You can go to a 2-phase AC motor in many applications. They tend to be a little cheaper. But yeah, and technically you can get away with 1-phase if you're in a bind. So it's just like with the DC motor where you have the magnetic field that is not as strong during parts of the rotation. You have to have at least 2 phases to get a continuous circular magnetic field. If you have only one, it isn't continuous, and you could get stuck, which would be bad. But so they don't really make them with 1, but technically you could do it, as long as you always had the ability to start it, some other mechanism. Okay, so there's a whole lot with AC motors, and I wish I had more time to talk about them because they are really cool. But for now, we'll stick to DC, and then we'll talk about these brushless DC motors. They're more similar to AC motors in that they have this rotating magnetic field, but they don't use AC power from the line. So you give them DC power. And what they do is they have sensors on them that tell them where the rotor is in its rotation, and that sensing is used to switch which coils around around the circumference of the motor are turned on at any given time. And so it's able to take DC power and switch it quickly, and there's me, it's frozen again, so that the field rotates around. So it's pretty. I would actually say that brushless DC motors are more complicated than AC motors. They're essentially AC motors, but you have to be really tricky on how you apply the AC or apply the power. So brushless DC motors, it sounds like they're just like DC motors, but there are no brushes. But in fact, brushless motors are AC motors, and what you're doing is just using modern solid-state switching electronics and feedback, like Hall effect sensors, to do a very complex control on an AC motor. And that's typically called a brushless DC motor. Really useful because the brushes don't wear out. They don't need as much maintenance. So I'm not going to go into the details of a mathematical model for brushless DC motors, but here's a reference that does go into some of those details. So now I'm going to compare the brushless to the brushed a little bit. So the brushed DC motor is still widely used despite its limitations, which include relatively frequent maintenance to replace brushes that wear out or replace commutators. Other disadvantages of brushed DC motors include their relatively large size, large rotor inertia, heat generated by the windings of the stator and/or rotor, and arcing that creates electronic interference for nearby electronics. So those can be issues that come along with a brushed DC motor. Reasons they are still widely used include that they are inexpensive, so these days they're about half the cost of brushless DC motors, so that's an advantage. They don't require, but often still use, complex driving circuits, so you can use a brushed DC motor with very little, sophistication in your driving circuit. You can pretty much just like turn them on and go. Brushed DC motors require that complex driving circuit. Brush DC motors are easy to model, and they're easily driven at different speeds. So for these reasons, an additional reason emerges: they're relatively easy to design with. So brush DC motors, even though they have, some drawbacks to them, they're really useful still, in part because they're just really easy to design with. Like we know how they work. We don't have to worry about the circuitry very much. And when you have fewer things in your system, the simplicity of your system actually is a big advantage in a lot of designs. So it's nice. So now, so cool looking. Okay, a PMDC motor model. So this is the permanent magnet DC motor model. So we have already explored a model for a permanent magnet DC motor in example 411. That was the very first lecture. That model assumed neither armature resistance nor inductance were present. That is, it was an ideal transformer model. A linear graph of a much better model for a DC motor is shown in figure 4.6. So here's the model in 4.6. So what we did before was just had this transformer that transformed energy from electronic energy to mechanical energy. And remember, transformers go both ways, right? So mechanical energy gets converted back into electrical energy as well. So let's actually stop and think about that for a minute before we move on with the details of this model. If you were to hook up say a crank to the motor on the mechanical side, or an engine to turn the shaft of the motor on the mechanical side, if you were to turn that shaft, what would happen on the electrical side? Power would flow this way, right? Because usually you use a motor this way, where you have a electronic energy, electronic power that flows to the mechanical side and delivers power. But you can actually run this both ways. And that is, what's the name for that? Yeah, a generator is typically, when we use it specifically for the application of generating electrical power from mechanical power, we would call that a generator. So a generator and a motor, a DC or AC, are actually the same device, just used differently. So, in the zombie apocalypse, you can take your blender motor out, turn it around, and charge your iPhone. You're going to have 0 bars, though. You can play Minesweeper. I don't know. What kind of games do you have locally on your phone that you play? Is that even a thing anymore? All the games are in the cloud.
We play games with Snapchat.
Yeah.
Or an iPhone and iMessage.
Yeah. Yeah, that'll be it. In the zombie apocalypse, texting, calling won't work, but iMessage will still work. It'll be good. I don't know. Oh, look, I'm back, guys. Cool. Hey, so generators and DC motors are very similar. Okay, great. So let's get back to our PMDC, permanent magnet DC motors. So this model that we've got here has the ideal transformer, and it also has a resistor and an inductor in series with the electronic side of the motor. So these are there to model the armature resistance and armature inductance. So that wire that gets wound, remember we said the armature windings, we end up actually coiling it many times around because we want to have more and more of that Lorentz force. So we want to have more and more current flowing through this region in the magnetic field. So we end up with quite a long distance of wire. And so that wire is going to have a resistance to it. And this might just be a couple ohms, but hopefully it is. Lower is better. The efficiency of our motor is better. We can run it at a higher torque and current if the resistance is lower. The higher the resistance, the lower current we can put in at max because we have this I squared R heating. And that heating is what tends to be the upper limit for our current. So we've got the inductance as well. We have a coil of wire. We're going to end up having inductance in that coil, just like an inductor is a coil, right? So we got to take that into account as well. So that makes it more realistic. On the other side, the mechanical side, we have put in a damping B and then a moment of inertia J. So the damping is there to model the bearings. So there's some loss. I mean, they're nice roller bearings, you know, they're as good as we can make them, but they're still going to have some losses. So the damping takes into account those bearing losses. And the moment of inertia is there to take into account the rotor inertia. So the rotor is, you know, it's got the armature on it, and it's itself usually made of steel. So it's got to give structure to the rotor, and it is in general a significant moment of inertia. So we have to take into account. So that is a more realistic DC motor model, and we'll be using this. We'll be applying this in the next lecture, actually. So the tail ends of R and 2, so this node and this node, are the two places where you're going to connect these up. So you're going to connect your motor up to some source, like you could have say a voltage source here. And here you could go maybe through like a flexible coupler to a load. Let's call this J2. That would be an example. So that's how we're going to connect it up when we actually put it into a system. All right. Motor constants. Let's talk about these. These cause a lot of confusion. So the motor torque constant, KT, and back EMF voltage constant, KV, are related to the transformer ratio TF derived above to characterize a brushless DC motor's response. If expressed in a set of consistent units, say SI units, KT and KV have the same numerical value and are equivalent to TF. Okay? Precisely, with consistent units, TF equals KV equals KT. That is something that is often hidden in a lot of presentations of KV and KT. However, manufacturers usually use weird units like ounce inch per amp and volts per kilo RPM. And when they do that, they have different numerical values. So if they're given in anything but SI units, we recommend converting to SI for analysis because it tends to cause a lot of confusion. Once in SI, we have something like, for X being some real number, we have KT being equal to X, and this is the torque constant, so it's in Newton meters per amp, and KV, the back EMF constant, X is, this is in volts per radians per second. And the reason that these are called, so they're the same numerical value, but the reason these things are called the torque constant and the back EMF constant is that the torque constant converts a current. So if you have the current on the electrical side, you multiply it by the torque constant, you get out the torque on the mechanical side. And with kV, if you have the angular velocity on the mechanical side, you multiply it by kV, you get out the voltage on the electrical side. So I used a term up here that we actually haven't used, but you do see show up a lot, so we should talk about it. Back EMF, or back EMF voltage. So in the way that we've framed this, like I said before, you can have power flow either direction in this through this transformer, right? This transducer gives us power flow either direction. So when you have a rotating armature in a magnetic field, you get a voltage that's generated on side 1, on the electrical side of the motor. So this voltage is called the back EMF voltage. So V1 is called B back EMF voltage. And notice that it's proportional to the angular velocity, and the constant of proportionality is kV. Okay, so the faster you go with this motor, the higher the back EMF voltage is going to be. And that's what's generating, well, that's what gives you your electrical power when you're rotating the mechanical side as a generator. But even when you're using it as a motor, there are certain cases when power will flow back into your circuit. So it is important to recognize that power can flow back into your circuit even when you use it as a motor. Say you spun the thing way up, then your circuit is going to have a little bit of power flow back into it when it starts to slow down. So there's that to keep in mind. Okay, so that's a little bit on KT and KV. Animations. There are some great animations of this stuff, and sometimes there's no substitute for seeing that sort of thing, like the three-dimensional motion of it. So I like this video here. There is an animation for a brushless DC motor that I like. I listed there. AC, asynchronous induction motors, synchronous motors, which they're very similar, but they're a little bit different in their operation. And also stepper motors is another sort of class of motors that you're going to see these days. There's a lot out there, and it can be a little bit intimidating sometimes when you look at all of these different options. I would say in broad strokes, think about brushed DC being cheapest in a lot of cases. When you get to really large industrial cases, you can't get brushed DC motors that are going to work, and you got to go to AC motors, which tend to be those are the largest motors that you can get. Are the big AC motors. Synchronous motors are better if you need precise control of speed. AC, asynchronous induction motors are cheaper and will do in most cases. Brushless DC, especially if you have a small application and you don't want to have servicing of that motor, brushless DC motors work really well. You can get a lot of torque out of them, and they don't require maintenance. They don't really wear out. Well, they still have bearings, so they do wear out eventually, but it takes a long time to wear out brushless. And And then stepper motors are really great for doing simple positioning of especially small stuff. When you're talking about industrial, big machinery motors, you're pretty much going to be in the AC motor area. You could be doing brush DC motors in smaller applications like driving a belt or something. You might do a brush DC. Big automation stuff though tends to be AC. Robotics and little stuff, you tend to be in one of the three: brushed DC, brushless DC, or stepper. One of those. Anything that needs to be mobile, where you can't be hooked into the nice three-phase power for running an AC motor. Anything that runs off a battery is going to need to be DC, right? So you can do steppers with DC, and you can do brushless and brushed DC. Yeah.
So is the difference, if you're running off of a battery,
Mm-hmm.
between the brushless DC and an AC motor, is the difference kind of like how you're changing the current?
It's kind of like the brushed DC is, the brushless DC has circuitry that effectively like makes the electronics look like it's AC to the armature. So it's instead of actually having AC power, what you're doing is you're switching your DC power around so that it looks like it's an AC power kind of. So that's the way you can think about it, at least.
So it's kind of like you're inverting it, but you're converting it like right on the stator instead of like before inputting it to the motor.
Yeah, exactly. I mean, it's like they took little AC motors and they were like, hey, let's take a DC signal and we'll just switch which coil it's going to so that it hits at the right time. It's pretty cool. Pretty much what it was I actually don't know the history of it, but they came on brushless DC brushless DC and stepper are the two that are the newest varieties. They both came on when solid state electronics became really cheap and fast, and also sensors became cheap because like the brushless DC motors, they use Hall effect sensors, which are really awesome, but they're relatively new technology to come on board as well. So the technology really allowed brushless DC to happen and stepper motors to happen. So yeah, switched power is kind of the key to those two technologies. So yeah, really cool. AC and brush DC, those were the three. So these three have the longest pedigree, especially asynchronous induction motors and brush DC motors. Those were like, when they started inventing motors, that's what they were creating. And DC and AC motors they have like a real elegance to them because they're somewhat simple in their operating principles. Like you can understand them relatively easily. And when you get into brushless and stepper, even in synchronous AC motors, the operation tends to get more and more complex, and you're relying on sensors and stuff, which you're not with these AC and brush DC motors. It's very like mechanical, which is cool. So I like the old like ingenious invention ways of looking at these things too. So I think that one of the things that's really sad about, I love control and measurement and feedback and all of this, but there's a tendency now when you need something to happen, you just go right there, right? You just think, oh, well, I'll do feedback, and then I'll measure where it's at, and then I'll control it with the motor, and we'll be good. Whereas back in the day when they didn't have that, they had to come up with all of these like tricks and cool mechanisms, and we don't even think about the mechanisms anymore now. We're just like, oh yeah, we'll just control it instead. So it's a little bit sad. I'm over it, but it's still a little bit sad. My friend has he's found like an old record player in his like dad's attic or something, and he was set it up. He refurbished it, and there was like a capacitor that had blown, and he replaced it. But it's really cool. He showed me the mechanism that's used to return the needle. So the head, the reed head on the record player, it gets fed slowly along the vinyl to the center, and then so you start on the outer edge, gets fed through the groove in the vinyl to the center, and then when it gets to the center, it returns to the outside. And like you might think, oh, okay, they probably have like a little feedback loop in there or something that's like saying, oh, you're this far in, you need to return now. Nope, it's mechanical. It has like, there's a little like, there are these gears that engage once the arm gets all the way to the end. It kicks in a gear that rotates it back to the outer edge and starts over. It's beautiful. These like vinyl gears. Oh yeah, this is cool. That was what I did over Thanksgiving. Was we were tearing apart this old record player. All right, cool. I should probably